Good evening. This is Miss Dagenford, and we are going to be looking at enzymes. And the previous video was about reactions, and so this is very much related. We know that reactions have an energy associated with them, an activation associated with them. And that activation energy means that most reactants don't have enough energy to go to the transition stage to go to the products. So if we have a bunch of reactants and they're all moving around, most of them are colliding, but they're colliding in a haphazard way. They're not, necessarily hitting each other in the right speed and the right orientation, and that means that most of them are not going to react. There might be the occasional one, like this one might hit with the right speed, in which case suddenly you've got a new molecule over here, yay. But overall, the amount of substrates per given amount of time is really low. Now, if we increase the temperature, if we did that, we would see more of them, but it still is not going to happen very fast. So along comes enzymes, and enzymes are something that you have heard before in honors biology. So hopefully there should be some memory coming back here. Now, enzymes, by far, we're going to look at, most of them are going to be proteins. But I'm going to say mostly because we're going to look at an interesting class of molecules that does have some enzymatic function. But the vast majority of them we're going to be looking at are going to be proteins. Now remember, not all proteins are enzymes, but the enzymes that we're going to be looking at, most of are going to be proteins. Now, a quick review: proteins are made of amino acids, and amino acids, as they join together, those amino acids can curl around and form these secondary structures. So we have the primary structure, which was the order of the amino acids. We have the secondary structures, which are the curls that can occur. The secondary structures are from the hydrogen bonds that can exist between the backbone of the amino acids. And so the hydrogen bonds are causing that alpha helix, and then you might have some curling around, and then you might have the beta sheet, and it keeps going. And so some of these are hydrogen bond interactions, some of these are ionic bonds. Now, if I keep going with this, and you just kind of get this grand superstructure of this molecule, and one thing you might notice is that eventually we start seeing this kind of interesting shape take place. And this shape includes this really tiny little pocket right here in the middle, where you might be able to get those two little molecules to sit in. And so this structure is extremely important. The shape, that three-dimensional shape, is going to create a little pocket called the active site. So the active site is where we're going to interact with the substrate. And if that active site disappears, then we got a problem, because the enzyme cannot work. So keep that in mind, because we're going to be looking at how that shape affects things, or what things affect the shape, sorry. So enzymes work on substrates, and substrates are what they either build up or take down or tear down. And enzymes increase the rate of the reaction, and they do so by decreasing the activation energy. So a very, very classic graph, and it's a good one to know. So here is our graph, and we're going to go back to that energy and then the reaction. And we have our, very classic reaction energy curve. And this little hill represents the activation energy, and oftentimes it is symbolized E sub A, activation energy. Now, without an enzyme, that activation energy is pretty high. With the enzyme, that activation energy is much lower. And what that means is the reactants, a lot more of them have the energy required to go towards the products, and so they can reach that transition stage. Now, so that's kind of right at that peak. We would refer to this as where there's this transition, and this is the point where the bonds connecting the substrates are unstable. Or if we're talking about connecting two things together, it's where the bonds start forming. Sometimes you'll see books using the molecules that are connected with wavy bonds, and that's showing the bonds are getting stressed. Or another example would be where you have two molecules that are starting to come together, and they're starting to form that bond. The electrons are shifting, and that's the transition stage. And so the activation energy goes lower, decreases. Now, how in the world does this work? It's kind of an interesting thing, and it goes back to that previous video. Now, just so you know, we have so many proteins out there, and that goes the same for the enzymes. The enzymes, there are so many enzymes, and they are specific to their substrate. So just as we had this superstructure up here, and if I made an outline of this superstructure of the protein, now you kind of get an idea of why books, when they draw enzymes, they just kind of look like weird little Legos, and so you get this shape of this enzyme. And so if that enzyme worked on these two molecules, you could get then a different enzyme. I'm just trying to be a little little different there. And you have this enzyme which might work on this molecule. And the other thing that some enzymes build, so this enzyme could create a molecule that is now connected together. This other enzyme could break this down, so as the substrates leave, they're now broken apart. So a nice review point from the previous video, which of these reactions, A or B, which one would be an anabolic, which one would be a catabolic reaction. Now, let's go back to that active site. So that active site, just so we know and review, that where I'm highlighting would be the active site, where it's interacting with a substrate. And here's where we put everything together. The enzymes have an active site that interacts with that substrate, and it's going to form temporary bonds. Now, that keyword temporary, that means it's going to be a hydrogen bond or an ionic bond, or you could be creating a little area that area is acidic, and that's what's going to facilitate the bonds being made, but it's going to be a temporary bond. And then that enzyme can then change the shape of its active site just slightly, and that helps interact with the substrates. Now, one important point is the enzymes are not going to bond permanently with our substrate. It is temporary, and that means that the enzyme is unaffected. It will be able to do this over and over and over again with new substrates, which means you really only need to have a few enzymes to have thousands of reactions with all the substrates. Now, we get to this idea of a lock and key interaction. And this lock and key ends up being this real important point. The lock and key is where you have that specific interaction with the enzyme and its substrate. So let's go back to my picture, and I'll probably not be able to reproduce it exactly, but here we are. So here we have the enzyme, and then in purple I'm going to draw the substrates. And the substrates are fitting into that active site. And we call that a lock and key, where they fit perfectly, just like just like a key into the lock. Now, because the enzyme can change shape ever so slightly, we can use a phrase called induced fit. We're inducing those substrates to have that right orientation. So just as the previous video showed, we're going to put those substrates in the right place so that bonds can form. So if I can, maybe I should zoom in just a little bit so you guys can see this. So I should have drawn that bigger. So the fact that these are held in this spot means that the bonds can, in that transition state, those bonds can be made. And just by shifting ever so slightly, they're going to present those substrate molecules so nicely together that those electrons just shift and into that transition state. And that activation energy is lower because those molecules are now just in that induced state that reduces the amount of energy that's required. Now this could be if it's an anabolic reaction where we're building them together. However, what if it's one that they're tearing down? Well, let me give you, for instance, let me go back to this. Let me just change, the idea. This time, let's say we're going to tear it down. We're going to break this. It's connected together. But by inducing that fit, by changing that molecule ever so slightly, you put tension and stress on the bonds. And think about like bending a toothpick. If I bend a toothpick, and that toothpick, it's not broken, but it's bent. But think about this. How much easier is it going to be for somebody else to come along and then break it? So think about that. I'm now reducing the amount of energy that it takes to break that. So by inducing that fit, that enzyme has reduced the amount of energy to break those bonds. So we're putting that stress on those bonds, and then that it makes it more stable for those molecules to separate, and then they go on to be the product. And so here's just a nice picture. Here's our enzyme, and the enzyme would be all around here. And then right there in the middle is where our active site is. It doesn't have to be big. That active site can be really, really tiny. Well, that is a nice introduction to enzymes. Hope that helps.